Okay, now let's solve several problems where we have to relate forces with the motion. And we will pick a couple of problems involving Cartesian coordinate system, and then a few problems where we will employ a tangent normal coordinate system as well as a polar coordinate system. And in doing so, we will apply our general method that we have studied for solving problems in this module, which relates forces with the motion. So this particular example is a solid example from the textbook. And over here, we have a crate of given mass. So let's start by writing down things that are given to us. So given is the mass, and that is of 45 kg. Okay. And then it's moving down the incline with the speed v0 equal to 8 meters per second. So we are also given the speed at a certain instant. With that, at the instant that the spring with elastic constant k equal to 100 Newton per meter is unstretched. So at this instant, the spring is actually unstretched, and the spring has a spring constant of 100 Newton per meter. So let me write unstretched here to indicate that this is the velocity when the spring is unstretched. Modeling the crate as a particle, determine the distance d the crate moves from the given position before it momentarily comes to a stop. So it says momentarily because there is a spring is going to be stretched and it will have a restoring force to pull the crate back up. So the question is, for the first time when it stops, at that moment, of course, the velocity, let's call it Vf, would be 0. So the question is, what is the distance traveled before it momentarily comes to a stop? Friction between the crate and the incline is negligible. There's no friction, and the unstretched length of the spring is L0. So L0 is given to you, and typically the unstretched length of the spring would be given with a subscript 0, and theta is for 25 degrees. So we know the angle theta also. So all these things are given, and we have to find, let me write here, find the distance traveled before it comes to a stop. Okay, so we'll start by applying our general method. In our general method, the step 1 is to identify the coordinate system that you will use. In this case, the choice of coordinate system is pretty obvious, primarily because we know something about the motion of this crate, which is that it's going to be moving down or up, right? That's the only motion that it has. So we are going to need only one position variable to describe the position of this particular crate, right? So we also call it a single degree of freedom system. A degree of freedom basically tells you how many independent parameters you will need to describe the position of something. So a crate like this is moving along a straight line. You need only one variable. If, let's say, there was a particle moving in a plane, let's say XY plane, it will need two coordinates. So that will be a 2 degree of freedom system, and so on. So we need to now decide where we are going to fix our reference frame. So I can fix my reference frame right over here, okay, and that would be all right. And that means the initial position of this crate would be the length of the spring, which is the unstretched length initially. But I don't have to really do that. What I can do is, assuming that this is the unstretched length at this instant, this is the initial instant, I can just fix my position variable and my coordinate system right here, okay? So after a while, the crate would move to some location, and it is going to be at a distance x, let's say, from the origin. So the origin of my reference frame is right at the instant when the spring is unstretched. And the reason I'm doing this is because I don't want to be bothered with the unstretched length. In all likelihood, this is not going to matter in this problem. Okay, so now what we do is we show our position variable, and this position variable is of course shown for a generic position, which means its initial position and final position. Let's say this is the final position when the Vf is 0. Okay, so somewhere in between we show our particle and we show its position with respect to the origin of coordinate frame. And this is the sort of approach that we'll be taking to solve the problems. Whenever you have a particle or a rigid body moving from one position to another position, what he will do is he'll pick some intermediate position, which is general position, and he will show what his position is. Okay, and of course that position is going to change over time. Okay, so step 1 is done. We picked our coordinate system. In this case, it's a Cartesian one. We showed it. We showed our position variable. The next step is to do kinematic analysis. So let's write that, kinematic analysis. So kinematic analysis involves basically computing the velocity and acceleration, right? So what is the velocity of this particle? It will be nothing but x dot I hat, right? Because we picked the x direction to be down the incline, and acceleration would be x double dot I hat. And at this point, there is nothing else we can do really in this. So we can just write the velocity and acceleration as a function of derivatives of position variable, right? So kinematic analysis, fairly simple. Next step is to draw free body diagram. Okay, so free body diagram would again be drawn at an intermediate position between initial and final. So this is the position we have chosen. So what I have to do is now draw this particle all by itself, right? Not show the incline or anything else. And we know this is making an angle theta. So what are the forces acting on it? We have gravity. We have normal reaction, right? There is no friction, but then we have force from the spring. So force from the spring is given by the spring constant times the deformation. So in this case, the deformation is actually a stretch. Now, since we fixed the origin of our coordinate system when the spring was unstretched, and now we're showing this particle at a position x, we know that the spring force would be k times x. Right? So that if you draw the free body diagram of the spring itself, the spring is a stretch, that's the tension. And this tension is equal to k times x. So from Newton's third law, the tension on the block is going to be in the opposite direction. That's why it is shown in that direction, right? So I'm assuming everybody knows what Newton's third law says. It says that for every force, there is an equal in magnitude but opposite in direction force that passes through the same point. So the forces are always collinear. Okay, so are there any other forces acting on this particle? None. That's it. Okay, so now we can apply Newton's second law. So first thing is, did we pick an inertial or a Newtonian reference frame? We did, because our frame is actually not moving, so we are okay. So sigma F equal to mass times acceleration. Now let's resolve all the vector components, all the vector terms over here in terms of the coordinate system that we have picked. So sigma F. So what are the forces along x direction? The forces along x directions are, so this angle is theta, so this angle is theta. So now let's write down these vector quantities in this equation in terms of their coordinates along x and y direction. So let's start with sigma F. So what are the forces acting along x direction? So we clearly have kx, which is acting along minus x direction, so that will be minus kx. And then we have mg, a component of mg which is pointing towards plus x, so that's mg sine theta, and that's pointing along I hat. And then we have n, which is along positive y direction, minus mg cosine theta, which is pointing along j direction, times acceleration, which is ax I hat plus ay j hat, right? In general, acceleration would have a component along x and y direction, both, okay? So from here, let's call this equation 1. From here, we can clearly see that acceleration is purely along x direction. That means that ay is really 0, right? So all we have on the right hand side is m times ax I hat. And on the left hand side, we have an x direction component and we have a y direction component. Since there is nothing on the right hand side, which is a coefficient of j hat, we can write this as 0 times j hat. And that means that this quantity is really equal to 0. So let's write that. So n minus mg cosine theta is equal to 0. And let's call it equation number 2. And we have minus kx plus mg times sine theta equal to n times acceleration along x direction. So those are the three equations that we have. So one we got from the kinematics, and then two we got from the Newton's second law, right? So now to be able to solve for the distance traveled when the velocity changes from 8 meters seconds to 0 meters per second, we have to be able to solve for acceleration from this, right? Okay, so the first equation that we have here, number 2, is just going to give us the normal reaction, which is not very useful. So let's focus our attention to equation 3. So what does it say? Equation 3 is, I'm going to write ax first, equal to mg sine theta minus kx. If I divide by m, I get g sine theta minus k over m times x. So that's our acceleration. And that's our main thing that we were looking for. So if you look at this acceleration expression, clearly we have a constant component here. G and theta don't change. K and m don't change, but x changes. That means acceleration is not constant. Acceleration is not constant, which means that even though you know this acceleration, you can't use Galileo's equations, one of the Galileo's equations, to solve for the distance traveled, right? So what do we do in this case? We know acceleration as a function of x. Now this becomes really a kinematics problem, what you did in the previous module. Since we are not interested in time, we are looking for the change in position as the velocity changes. We are going to write acceleration not as dv over dt, but using the change of rule for the variables, we will write this as this, right? Using the chain rule, and we get v times dv over dx, and that is equal to g sine theta minus k over m x, right? Now it's a simple matter of integrating it. So v dv equal to g sine theta times dx minus k over m integral x dx. I brought the k over m outside because it's really a constant. Same thing over here. So x changes from 0 to d. We're looking for, change from 0 position to distance traveled d. This is changing from some initial velocity to final velocity, which actually is 0, right? Because it comes to a stop. Okay. So what do we get here? This is 0 minus v0 square over 2 equal to g sine theta times d minus k over m times d square. Okay, so let's rearrange this a little bit. So k d square minus g m sine theta times d minus v0 square over 2, and m goes here as well. So I'm multiplying by m everywhere, and then I'm rearranging this, so we get this quadratic equation, right? So this is a quadratic equation in d, right? So here we have d squared, and here we have d. Rest of the things are known to us. So if you substitute the numbers that are given to you over here, essentially all these numbers that are given to you, you substitute them in here, and you get a quadratic equation. It's a quadratic equation, you can solve it. So in general, it'll give you two solutions, right? 1 and 2, and one of them may be acceptable, the other one would not be. So for example, if d turns out to be a negative number, then let's say this one is negative, then you will reject it, while this one may be something like, let's say 5 centimeters or 5 meters, depending on what the input and numbers are, then that's the one that you will accept.